and then we multiply from R3 minus 1 from the right here. And that's almost what we had, what we wanted. A times Q3 equals Q3 times something plus rank 1 correction. And both of these terms, they have special structure. So the rank 1 correction is this. So it's still, since we multiply the row of the identity matrix, and this is an upper triangle matrix. The inverse of an upper triangle matrix is still an upper triangle matrix. And if you multiply this row by an upper triangle matrix, we still get the last row, which is 0, 0, 1. So it's some gamma times the last column of the identity matrix. So this is more complicated. But if you check, you get an upper Heisenberg matrix. For 3 times 3 is not so astonishing, because you get only 1 0. But in general, you will get zeros below the second diagonal. So it will be upper Heisenberg if you generalize from 3 to n. So what we have got? We have got the following formula that the orthogonal basis for the Krylov subspace satisfies this relation, which is almost Arnoldi relation up to, remember there was this parameters alpha, now we will find them. So basically, this is okay, AQJ, QJ upper Heisenberg, plus something, and this thing is the difference between the true Krylov vector minus the linear combination of all previous Krylov vectors. So what we want to do, we select these coefficients in such a way that this new vector is orthogonal to all the vectors in the previous Krylov subspace. So in some way we mimic this orthogonalization. And what it means is it lies in the Krylov subspace and it is orthogonal to the basis of the previous Krylov subspace. It means this is the last column of Qj plus 1. The difference between Qj and Qj plus 1 is exactly this vector. So that was one of the tough parts of today's lecture. But this is the Arnoldi relation, which is very important. AQJ, Qj plus 1 plus some coefficient times the new vector. And this is the crucial formula, in fact, for the efficient generation of such subspaces. Because basically, to generate, you can just take this equation, solve one by one, and get the Qj. And you will get the new Qj as the product of A to something. So in the non-symmetric case, this is just modified Gram-Schmidt applied to the Krylov subspace. But we are talking about Hermitian case, we're talking about symmetric case. And everything is much simpler. This is upper Heisenberg thing here, but for the symmetric case, have this equation. So what happens if you multiply this equation from Qj star from the left? If you multiply this equation by the Qj star from the left, this will be Hj, and here we will have Qj star Qj, which is zero by construction. So we have Hj, just this Qj star AQJ, Galerkin projection. So if A is Hermitian, and this is upper Heisenberg, this is also Hermitian. It means this is tridiagonal in symmetric case. So the matrix you get in the Hermitian case of this process is a tridiagonal, and this gives you the opportunity to construct the next vector of the orthogonal basis in the Krylov subspace without constructing the full basis. And let's see how. This is a called Lanzas process. So for the symmetric positive definite case, you have the same relation, but here we have tridiagonal matrix. Let me fix again my slides. So, and we want to find Qj. We already know this, and we want to find Qj. So we just need to compute the last column of the difference here. And you see that the last column of the difference is just a Qj minus 1 minus some coefficient times Qj minus 1 minus some coefficient times Qj minus 2. And that's all. Because this is tridiagonal, there will be only two previous vectors. So the next vector is a linear combination of A applied to the previous vector, minus the previous vector, and minus the previous vector. Only two vectors. Okay? And what we need to do here, so this can be recovered from normalization, we need to find these two coefficients, but we have orthogonality conditions. So this vector has to be orthogonal to Qj minus 1, and this vector has to be orthogonal to Qj minus 2. And this gives you exactly two equations for two unknowns. Take a scalar product, boom, you get the equation. So for example, this coefficient would be a scalar product of a Qj minus 1 times Qj minus 1, divided by the norm of Qj minus 1, which is 1. And the same for this. So you get two equations. And the exact arithmetic, what you get exact orthogonality to all the previous vectors. Due to the tridiagonal property, you get exact orthogonality to all the previous vectors. So we only need to store two previous vectors. This is the beauty of short-term recurrence relation, to get the next vector. So we don't have to orthogonalize to the previous. Of course, if you do it in the floating point arithmetic, you may get the orthogonalization may get lost. There are some ways of dealing with that and so on, but in exact arithmetic you exactly get this